Nice to see you. How was your weekend? Ready for new week? Let's start with short discussion of our previous lecture. So we have shown recently that if we have a closed loop of current in uniform magnetic field, then net force is equal to what?
Zero.
Zero. There is no force inserted on this loop. However, if we consider exerted torque on this loop, then we already get some not equal to zero net torque. How do we calculate this net torque? We derive equations for that.
Current multiplied by vector of area and vector of
Magnetic. So it's product of magnitude of electrical current which flows through the closed loop. Then we have cross product of two vectors, area vector and magnetic field vector. How we define area vector? It is the magnitude of this vector is equal to the area of the loop, and direction is defined by the, so it's always perpendicular to the plane of this area of the loop, and determined, the orientation is determined by the direction of current flow, either clockwise or counterclockwise. So we show this right-hand rule in order to determine the orientation of area. We also introduced another parameter in order to simplify this equation. So another parameter was magnetic dipole moment, which was equal to, so it's like mu vector. Current multiplied area vector. And that gives us the magnetic dipole moment. And in terms of magnetic dipole moment, the exerted torque on a loop, closed loop with current placed in uniform magnetic field will be determined as just cross product of mu vector and B vector, magnetic field vector. What are practical implications of this torque exerted on current loops in magnetic field? Electrical actuators, so we can transfer electric energy into mechanical. Any other applications?
that we needed to measure flow of the current.
I mentioned about this option to use it in ampere meters to measure magnitude of electric current flowing in electric circuit. In that case, we connect this internal current loop placed in uniform magnetic field in series to the electric circuit where we want to measure current. By the way, what should be the resistance of this current loop for such application in current measurement? We didn't mention about that last time, but if you think about it, what should be resistance of an ampere meter with which we measure electric current? Ideally should be equal to zero, but that's impossible. That's why we want to make it as small as we can in order to minimize the effect of the ampere meter as a measuring unit instrument on the magnitude of electric current in the circuit where we want to know the electric process. Okay, so now we go to another topic which provides more information on sources of magnetic field. Because so far we considered how charged particles are moving in magnetic field and what forces are exerted on these charged particles. However, we know already from previous discussion that magnetic field is also created by mobile charges, and we want to know how we can calculate the magnitude and orientation of magnetic field vector next to some uh, mobile charge carriers. So most common for us is to consider some conductor through which electric current is flowing and deal with this as a model system. So that's what we will do, but keep in mind that that is also valid for any fluxes of charged particles. So if there is some flow of electrons or protons, some like electron beam, that would also be considered as source of magnetic field, and the same principles will be applied to this case as we will develop considering some electrical conductor with current. So that's our model system. We have some conductor with electric current floating through it. So we have some length element which will be represented by ds vector as some small element of this conductor. And we have, let's say, some point P in the space around this conductor next to this element, length element ds. We can characterize this with some distance r, the position of this point P with respect to considered element, length element. Here also we can draw a r unit vector, which will define the orientation from this length element towards the point where we want to determine magnetic field. Once we have all these parameters, so-called, we will consider now so-called Biot-Savart law, which will allow us to determine magnetic field created by this length element with electric current. So in its time, Biot and Savart, two scientists, they were trying to understand how magnetic field created by electric current in conductors interacts with permanent magnets. And over many experiments, they figure out the following statements, which are true for this type of interaction. So let us consider them first. So magnetic field vector, we will call dB vector, created by this small element ds, will be always perpendicular to the ds vector in point P, and also it will be, this dB vector will be perpendicular to unit vector r, which defines the orientation which defines position of point P with respect to the length element ds. So that is shown in terms of orientation of vector dB, and magnitude of this vector dB, magnetic vector, will be proportional to 1 over r square, so proportional to the distance in the power minus 2. Then it is also proportional, we can write it here, dB proportional to the electric current which flows through the circuit, or like this electrical conductor. And on top of that, we also have that dB is proportional to the magnitude of this length element ds. So the larger length element, also this considered longer length element, we see the increase in magnitude of magnetic field. However, there is one more thing, and that is that magnitude of magnetic field vector is proportional to sinus theta, where theta, can write it here, theta is the angle between ds vector and r unit vector. So taking this into account, we already might see some, first of all, similarities with Coulomb law, because interaction between two charges, or if we consider electric field created by electric charge, also proportional to 1 over like r squared. However, in this case, as we already know from comparison electric and magnetic field, there are differences in orientations. So here it's a little bit more complicated and not so straightforward, not along the r unit vector direction as we have in the case of point electric charge when we consider electric field created by this charge. So that's why when you summarize all these findings together, the equation which can describe this dB vector created next to element length ds vector with electric current I will be described as follows. So this will be dB vector is equal to mu naught over 4 pi times I times ds vector cross product r unit vector divided by r squared. So this is technically the Piot-Savart law. And here this mu naught is the permeability of magnetic permeability of free space. It is given as 4 pi times 10 in the minus 7 Tesla times meter over ampere. So this is a universal constant. We have universal constant, we have magnitude of electric. The orientation, as we see here, is perpendicular to both of these vectors, and that's true because it's given with this cross product. Every time when we have cross product of vectors, the resultant vector will be perpendicular to both of them. Then it's proportional to 1 over r squared, the magnitude, that's true. Proportional to current, that's true. Proportional to magnitude of the ds vector, that's also true. It's in numerator. And magnitude proportional to sinus theta, that comes from the features of the cross product. Because magnitude of the cross product, we can write it here. Say we have two vectors, a cross product b vector, and magnitude of this cross product will be magnitude of a vector times magnitude of b vector times sinus theta, which is the angle between two vectors. So that you should remember from previous course of physics 161 and mathematics also. So now we have the expression which defines the magnetic field created by this given small length element. However, as usually, we want to know how magnetic field in given point P is created by whole conductor or some large segment of this conductor. So in this case, obviously, we need to integrate this expression in order to get resultant magnetic field from all conductor in this point P. So in this case, we can write, let's write it here, that B vector will be equal to mu naught times I over 4 pi. These are constants which do not change as we move along the conductor because current is the same. Then we have integral over this expression ds vector cross product r unit vector over r squared. So that is the general equation, how we determine magnetic field under any circumstances when we have any type of conductors. It is possible to determine magnetic field vector magnitude and orientation. Let us consider some examples of application of this important Biot-Savart law, because as you may feel already, that's quite important because we can determine magnetic field vector at any point next to a conductor with electric current of any shape, or also valid, as I mentioned earlier, for the case when we have just some beam of electrons or protons in vacuum or in other material. So let us consider such a system. X, Y, and Z system of coordinates. Here we have, let me change the color, a straight conductor which is aligned along axis X. Let us consider at some coordinate which will be like minus X, length element ds vector. We want to determine what will be the magnetic field created by this ds vector, considering that some electric current I is flowing through this conductor in point P located on axis Y at coordinate, so its position with respect to the origin of the system of coordinates will be, let's say, A. So we want to know what will be magnetic field vector, dB vector, at this point. So that is our question we want to answer. So now we can also show here this distance r from the length element to the point where we want to determine magnetic field vector. We can show here also r unit vector, which defines the orientation of point P next to ds length element. And also we can consider this angle theta between the orientation of unit vector r and axis y. So now let us first determine the cross product of. So we remember this equation. Actually, we want to look first at this equation because we are dealing with dB vector. Let us write it
down here so we can see it. dB vector is equal, here's my dB vector, mu naught over 4 pi times I times ds vector cross product r unit vector divided by r square. So this we remember here. And now let us determine the product, cross product of two vectors, ds vector times r unit vector. So first of all, what will be the orientation? And that actually will define the orientation of this cross product, resultant vector of cross product, and that will define orientation of magnetic field vector. So we cannot tell anything about the magnitude so far, but how do we multiply two vectors with cross product? With the rule of right hand, we turn this vector ds towards first vector towards the second vector, and then the right hand sum will show us the orientation of the resultant vector of this cross product. So in this case, it will be a line along axis z perpendicular to both vectors. So we can write it here. So this is the orientation of dB vector. So if we look at this plane of the image, dB vector, so it will be coming out from the plane in this point P, next to point P. It will come out from the plane of the image and goes along axis Z. Here we can also show K unit vector to specify the orientation of axis Z, and that will be easier for us to determine for the orientation, to define orientation of magnetic field vector. So here we can already put this K unit vector because we know that it will be along axis Z. And probably no, it's better to do it. So it will be, let us consider magnitude of this ds vector cross product r unit vector. And here will be k unit vector. So this will be correct. And now we need to determine what will be the magnitude of this cross product. Since ds vector is aligned exactly along x, we can, when we consider its magnitude, we can just put it as dx, because it is aligned only along axis x. All other projections will be equal to 0. So we can write here dx. Then what is the magnitude of unit vector r? No, but from name already we know that unit vector magnitude is unit. So it just defines the orientation of point P position with respect to the ds vector. It's the same as k unit vector. Its magnitude is unity, but it defines orientation. So we just don't write it because it will be unity. And then what else we have in the cross product when we determine magnitude? Sinus of the angle between two vectors. So what will be the angle between these two vectors? ds vector and r unit vector. As is this one. So it will be, no. So it will be 4 pi over 2 minus theta. pi over 2 minus theta. And we don't forget about this k unit vector because it defines the orientation of the cross product. We can write it in simplified form, so it can be written as dx times cosinus theta times k unit vector. Okay, so this part we already have, which gives us the magnitude of cross product. And following this general equation, let us write expression for the dB vector in this point P. So this will be mu naught over 4 pi times I. Instead of the cross product, we put dx cosinus theta. In the denominator, we have r squared, and here we have k unit vector. So that is our expression for the dB vector created by this segment ds vector. In order to proceed further and determine magnetic field created by the whole conductor, as we show here, because so far we determined magnetic field vector created only by this small segment ds vector with the length dx. So we answered the first part of the question when we consider this ds length element. However, usually we want to get the contribution of many length elements which form the whole conductor and determine what will be in this point P the magnetic field vector B. So in order to do that, we need to express dx and r, these linear dimensions, in form of theta in order to proceed further with the integration. So what will be the distance between point P and ds length element? So this is our r, this dashed line. We know that point P is placed at distance a from origin of the coordinate along axis y. So this is kind of a hypotenuse of the right angle triangular. We know angle theta, so r can be expressed as a divided by cosinus theta. Now let us determine what will be x, the coordinate, the position of this length element ds. So x will be equal, here we put minus because it is in negative part of axis x, and this will be a times tangent theta. So this all comes from this right angle triangular which we deal with. However, once with r we already solved the question, so we have the representation in terms of theta. However, with x we have here dx, so we need to take differential of this. So dx will be equal to minus a times d theta divided by cosinus squared theta. So we kind of take derivative of a times tangent theta, derivative of tangent theta gives us 1 over cosine squared theta. That's from the table of derivatives. And multiply by derivative of independent variable d theta in order to get this differential dx. So now we have what we need. We need only to substitute these expressions into our equation. So what we get finally, this will be db vector equal to mu naught over 4 pi. Then we have I, magnitude of electric current. Then let us replace dx. That will be minus a times d theta over cosine squared theta. Then we need to replace r square, like 1 over r square. So in this case, it will be cosine squared theta over a square. Then we have still cosine theta and this unit vector k. Okay, so now we have pretty much everything what we need to do. We need only to define what will be the range of integration in order to get the contribution to magnetic field from the whole conductor. So let us draw this system like simplified in order not to have too overcrowded image. So we have axis x and y here, and here is our point P, where we want to determine magnetic field vector, resultant one. This is our conductor. And how we define the edges of this conductor. So here is one angle, theta 1, and here is another angle, theta 2. So what we need to do in our integration of this expression which we obtain, we need to integrate from theta 1 to theta 2. Let us do it. So it will be B vector, resultant magnetic field vector, at this point P will be equal. We can factor out all constants. So this will be, let's see first maybe what we have. A and square, we cancel out these guys. So eventually we have mu naught, also minus we can factor out, mu naught times I divided by 4 pi times A. Here is integral from theta 1 to theta 2 of cosinus theta d theta. And we forgot k unit vector. Also factor out from the integral. So what will be integral of cosine theta? Oops. Sinus theta. Okay, so we have minus mu naught I over 4 pi A times k unit vector. Here will be sinus theta from theta 1 to theta 2. Taking into account this minus in front, we will get mu naught times I over 4 pi A times sinus theta 1 minus sinus theta 2. and we multiply it by unit vector k. So that is the answer to the question. What will be magnetic field vector at point P, which is the resultant contribution from each length segment of this conductor. Now let us consider some special case when this conductor is infinitely long. So what it will give us? If this conductor is infinitely long, let's say it goes like very far, like up to here, and goes in the other direction, and doesn't end even. So what will be these angles of theta 1 and theta 2, which define kind of the infinitely far beginning and infinitely far end of this conductor? It will be pi over 2. It will be like 90 degrees. It will be just, yeah. So in this case, what we get for magnetic field for such infinitely long conductor, straight conductor, it will be mu naught times I over 4 pi times A, which is the distance from the conductor to the point where we want to determine magnetic field. And here will be sinus pi over 2 minus sinus minus pi over 2, because they will be just in different directions. So this will be unity, and this will be minus 1. And eventually we get mu naught times I over 4 pi times A, and here will be just factor of 2. Eventually we get mu naught times I over 2 pi A. So that is the, and again we can put here k unit vector in order to define the orientation. So we have the magnitude of magnetic field created by infinitely long conductor, straight conductor, which is also given with the orientation of the ray. So this magnitude is equal to mu naught times I, and divided by 2 pi times A, the distance between the conductor and the point where we want to determine this magnetic field. So let us consider one more example when we have a curved conductor. So let's say we have conductor in the form of a segment of a circle with some radius a. So this angle is theta. Here we can determine some ds vector, length element, and this will be our r unit vector. So in this case, the angle between ds vector and r unit vector will be always equal to pi over 2, 90 degrees, because this is a segment of a circle. So we can write for dB magnitude of magnetic field in the center of this circle as mu naught over 4 pi times I ds over a square, because distance from this length element to the center will be a. Then the product ds vector and r unit vector will be just magnitude of ds, because both r unit vector is unity and sinus of pi over 2 is unity, and that's what we actually get. So if we want to determine the magnetic field created in this point in the center of the circle, of which this segment is, we need to integrate so the magnitude of magnetic field, which will be oriented in this case perpendicular to the plane of the image, will be equal to mu naught times I over 4 pi a square integral ds. So that is just the length of the segment, because integral over ds, it will give us the length of the segment. And mu naught times I over 4 pi a square, Here is the length of the segment, and keep in mind what will be the length of the segment equal to in terms of angle. We have this relationship with angle, angle in radians and radius. So the length of the segment will be equal to angle theta in radians times a, the radius of the circle of which segment we are discussing. So we can substitute it with theta times radius of the circle. Can write it mu naught times I over 4 pi a square times a, and here is theta. So a and a square cancel out. Eventually we will get mu naught times I over 4 pi a times theta. And now let's say we have a coil. So we have a conductor which is filling all this circle with some electric current I. So obviously we want to show some current I. So here is current I. Here is the radius A, and we want to determine what will be the magnetic field vector, like what's the magnitude of magnetic field in the center of this circular conductor. So here we need to consider this angle theta. So we kind of integrate this over the angle theta from 0 to 2 pi, because we go from for all circle. And in this case, we will get the magnetic field for closed circular conductor, like loop, just full coil of conductor with current, and magnetic field in the center of this coil will be given as mu naught times I over 4 pi times A, and we need to multiply it by 2 pi, because that is the angle. So we integrate from 0 to 2 pi. So here we cancel this, we get 2, we cancel pi. And eventually we get the mu naught times I over 2a. So that will be the magnitude of magnetic field created inside a coil with electric current I and radius a. So now let us summarize our discussion for today.
as I mentioned in the beginning, we so far discussed how electric charges interact with external magnetic field. However, it's time to analyze how magnetic field are created, means to quantify sources of magnetic field. And Biot-Savart's law is the equation which allows us to determine magnetic field vector magnitude and orientation next to a conductor with electric current. So regardless of the shape of the conductor, we can always consider some small length element. With respect to this small length element, we define magnetic field vector created by this single length element, and when we want to determine the resultant magnetic field vector created by whole conductor, we integrate all over the conductor. So the magnetic field vector is proportional to magnitude of electric current which flows through the conductor, is proportional to the magnitude of the element length, which we consider reversely proportional to 1 to r squared distance from the length element to the point where we want to determine the magnetic field vector, and its orientation is defined by the cross product of ds vector and r unit vector, where r unit vector defines the position of point P with respect to chosen length element ds vector. Thank you very much for attention. We'll continue with magnetic field next lecture too. So see you on Wednesday.